last but not least, we have Wilko, who used to be a drug designer. He did not bring samples today. So he's going to be telling us about the drugs he was designing and about making drugs, not war. A little bit about what he was doing in Australia and beyond. So,
all right, so I'm the person tonight, so just be a bit patient, you'll be free very soon. And I wanted to get you disappointed right away. This is not going to be about recreational drugs. It's not about the molecules that make you happy. But still, in a way, it's about molecules that don't cure diseases. So I hope that will make you a little bit happy. Now, what I want to take a few minutes for today is, what I'm really hoping I can challenge your mind a little bit about the way we make and we use drugs to fight infection or infectious diseases. Because I think we can't find better ways than the old ways. And to start with, you're all familiar with antibiotics. You very certainly have taken antibiotics in your life many times when you get an infection, a cold, whatever your doctor told you to. And antibiotics pretty much literally means killing life. And that's what the drug does. It kills bacteria. Straight and simple. You might have heard about probiotics, which means, on the opposite, pro-life. And these usually are nice, healthy, good bacteria that you take preventively. So they go and live in your guts and take up all the space, nice and cozy, so when an infectious bacteria came in, it has no space to grow. Basically, you're trying to outcompete the infectious bacteria with the good ones. And what I want to talk to you today about is drugs that are neither antibiotics nor probiotics. They are not killing life, but they're not pro-life either. They're called antivirulent drugs, and I'm hoping I'll be able to convince you that they're really cool drugs. Like, I think they're really nice. But for a bit of background, you must have heard before that this issue with antibiotics and antibiotic resistance right now, because we've been using antibiotics for 70, 80 years now, but everywhere, all the time. Every time you have a little bit of a cold, there's a good chance your doctor will give you antibiotics. We use them for animal feed because it promotes growth and prevents disease. We use them in the environment as well. We use them all the time, so much that no bacteria has developed a way to protect themselves against drugs, which we call antibiotic resistance. And it's up to a point that even the famous penicillin, which was discovered by Dr. Ian Fleming back in 41 or 42, is by today pretty much completely useless. Everything everywhere will be resistant to that antibiotic. You might also have heard the term superbug, which has been thrown all over the place over the past few years, and for a good reason. And superbugs are bacteria which are resistant to 1, 2, 3 or more antibiotics. So it's getting harder and harder to kill them because they're becoming immune. And even a few years ago, there was quite a big scare because some scientists described the first bacteria which was resistant to every single antibiotics we have discovered for 80 years. Basically, we cannot kill this bacteria with treatment. It's invincible. And luckily for us, it was a bacteria which is harmless for you, but it means any infectious one, any pathogenic bacteria, which will be resistant to everything, might be just around the corner. So it's a kind of a scary situation. And because it's harder and harder to kill bacteria, we now have to use more and more what we call last resort antibiotics. And they're called last resort because they have really big drawbacks for your health. And basically, the last resort antibiotics are what we call broad spectrum, which means they are so powerful they will affect a wide range of bacteria. They will affect many bacteria, the good ones and the bad ones. And knowing you have up to 1,000 different species of bacteria in your guts, there's actually more bacteria in your guts than you have cells in your body. So if you have 3-4 billion bacteria in your guts and you use one of these last resort antibiotics that pretty much kill everything, this is what happened to you in your guts. You just destroy everything. It's like a nuclear weapon. It doesn't make a difference between civilians and military. A last resort broad spectrum antibiotic will kill indistinctively, hopefully the bad bacteria, but also all the good healthy bacteria in your guts. And that's really bad, because there's good bacteria, beyond helping you with digestion and your daily life, it's actually the one that also is your primary line of defense against other bacteria, because they sit there, they occupy all the space, so when infectious bacteria want to come in, there's not much space to set them. So if you wipe them out, or almost, with an antibiotic, and clean slate, the space for everybody, who's gonna come? More infectious bacteria. And that's very common, it's called secondary infection. So you get sick, you take very strong antibiotics to get better, and then you get sick straight away, because more bacteria use the free space to get in. It's even worse than this, because you wipe out everything, you also kill some bacteria that prevent you to have allergies. So you might end up with allergies that you never had before, and you have to carry on to the rest of your life. It could be peanuts, it could be seafood, something, but the bacteria that help you digest this is gone due to the antibiotic. So then you have to restrict your lifestyle just because you try to cure disease. Also, another side effect is if you wipe out bacteria in your guts, you're gonna get really depressed. I'm not gonna go into details about it, but it's been shown you'll be really depressed if you just kill everything. So, obvious question is if we want to avoid using these last resort antibiotics because there's a big price to pay and it will take you months to recover from it, why don't we make new antibiotics? Why we just don't keep making new ones so we don't avoid using the powerful ones? Well, the issue is we can't. We've been pretty much exhausting all the sources of natural antibiotics in the world for the past 80 years now, and we found maybe 1 or 2 new antibiotics every decade, and this is no way to sustain constant treatment for everybody in hospital or everybody who has a cold or anything. And the whole thing is, with this antibiotic resistance that keep appearing, is right now, they discovered that when they develop a new antibiotics, and developing a drug take up to 20 years, and that includes laboratory research, animal testing, and human clinical testing, they figured out that when they keep to an hospital and try some trials on human, within 6 months, resistance appears. And then your antibiotics is good to go to the bin. We're talking years before it even gets to the pharmacy on the shelf. It's just you try to test it, within 6 months, to the bin. Hasn't even cured anyone yet, it's too late to bacterial resistance. So, looking at this huge problem that's going to be just even worse in the future, some scientists decided to take a step back and think about the way we make drugs. And they actually went to dig of an idea that was first looked in the late 1800s, even if at the time they had little clue what they were doing, but now with more research on DNA and microbiology, we have a better idea. And they went back and they would start thinking, well, with all this antibiotic resistance happening everywhere with bacteria, why does it appear? And in a very simple way, maybe bacteria become resistant to the drug because we're trying to kill them. This is the aim of an antibiotic. We kill, we aim for the DNA, we just want to kill it dead. So of course the bacteria will try to mutate in order to survive. It's basic evolution. You're being present, how can you mutate and find a way to survive? It's a very strong evolutionary pressure. And so scientists were thinking, well, what if we break the cycle of violence? After 7-8 decades of warfare, is there a way to just make peace with the bacteria? Is there a way to have a violence-free solution to the whole arms race? And basically, yeah, so just to explain, you just imagine a neighboring country has missiles and tanks and even nukes. Of course, you're going to try to find a defense against that, and when you find a solution against nuclear weapons, you're going to share the technologies with your closest allies, so everybody's protected. That's exactly what the bacteria does. There's a weapon, they find a protection, and they share it around. So if we can stop this, we might have a solution to stop the outbursts of resistance. And so some scientists went to look into what I call the hippie medication, and you might think it's a bit of a hippie idealistic dream, but it's actually quite interesting the way it works. And there's a one we call antiviral drugs, and I would like you to think about them much more like a UN peacekeeping mission. These drugs will go into, like a country at war in your guts, but they will go and just take weapons away from the bacteria and say, you cannot cause this anymore, you cannot secrete toxins anymore, you cannot start an inflammation, they just taking the weapons away, maybe, for example, to keep the analogy, start a denuclearization program into that country, the bacteria. They're not trying to topple the governments, they're not trying to invade that country, the bacteria, they're just leaving the bacteria happy, alive, so good, we're not trying to kill you, we just want to make you harmless and completely inoffensive for the human. And if we can make this, well, there's multiple advantages. First, no more disease. But second, if you make antibiotics that does not kill anymore, not only you're not killing the bad bacteria, but you're not also killing the good ones. So it means your healthy one in your guts will be fine. So no secondary infection, no new allergies, no depression, nothing. So it looks like a really good drink. And actually, there's quite a renewed interest in the scientific community for this reason. Don't try to read the graph too much, just show how much interest there is in the scientific community in terms of reports and papers and technological progress. And there's now quite a few drugs making their way slowly to clinical trials. Once again, don't bother reading everything, but these drugs can work in many different ways. I'm going to try to explain, once again, in a simple way. We're not going to go into details. But how can you stop a bacteria from being infectious without killing it? Well, first, you can straight away target, for example, the toxins. You might have heard some of the toxins that are really harmful, for example, from Clostridium botulinum, which leads to botulism, or for example, from Bacillus anthracis, which causes something called anthrax, that might ring a bell. And the idea is, instead of targeting the bacteria itself, you just target the toxins. Once again, you're not touching the bacteria, you're not trying to kill it, bacteria has no reason to develop any resistance to it, just preventing any disease to happen. Or you can also prevent the bacteria to stick to anything. For example, in the case of multi-resistant Staphylococcus aureus, the golden staph, that might also ring a bell, they found a way to stop it from starting any disease, is to stop it from sticking to the cells that lining the wall of your intestine. So that way the bacteria cannot stick anywhere and is not able to inject any harmful toxins and is not able to hide from the immune system anymore. Once again, we're not touching the bacteria, we leave it happy and nice, we just prevent it to stick anywhere and it becomes completely harmless. Another way is to jam the communication between bacteria. One bacteria is completely harmless to the body. 10 millions, 100 millions, that's another story. And now we know from recently that bacteria can communicate with each other to organize a synchronized action. But this has happened because 10 million bacteria decided together, let's produce toxin, let's infect this host, let's start this disease. So if we can jam the communication between the bacteria, which happens through molecules floating from one to the other or happens through these little tubes, if we stop this, each bacteria thinks it's alone. And the bacteria alone is not able to start any disease. So once again, we're not targeting the bacteria, we're leaving it alone, we're just jamming the communication signal in between in a way that the bacteria has no reason to become resistant, it's happy and still alive. So the fifth way that's being developed right now is also all this weaponry need to be assembled in 3D, like a bit like a 3D printer. But if you can inhibit, if you can stop that 3D printer, then this weapon doesn't actually exist at all. And so there's many different ways to do this, and some drugs right now are making, as I said, their way to clinical trials, quite successful. But it's not all pink, and in science there's no miracle cure anywhere. It's not going to be saving humanity anytime soon, because they unfortunately have some drawbacks. None of these drugs have made it to the shelf of the pharmacy yet. Still takes 20 years to develop a drug, so we're halfway there. But there's some issue with these drugs. Is first, we don't know what happened when you start taking the drug. Let's say you take the start treatment, you take the drug, bacteria turn harmless, everybody's happy, then after 2 weeks you stop. Is the bacteria going to turn back to the harmful version? We don't know. What is going to happen to the bacteria in between? Is your immune system going to be able to kill it? Is it just going to be flushed over normally? We don't really know. The other issue is, while antibiotics usually act in a more broad way, they will target the DNA or they will target something critical for survival. Trying to neutralize a weapon is very specific. So we have to make a very specific drug to target this very specific weapon from this very specific bacteria. So the big challenge is to know which bacteria is actually causing a disease in your body. And that's something we have a lot of trouble to do even today in medicine, to figure out which bacteria is actually causing the disease. That's why they give you antibiotics that kill everything. At least we know the bacteria is gone. But in that case, we need to know. So we need to have better diagnostic and find a way, okay, it's this specific bacteria, let's inhibit this specific weapons. We have another issue. What if a bacteria has multiple weapons? So you have to take a drug for every single weapons? That's going to be a large cocktail of drugs to take every morning for 2 weeks. And then we can get bigger than that. What if you have different bacterial species causing an infection at the same time? So you need one drug per weapon per bacteria. You might end up taking 10, 15, 20 pills at the same time to control everything. So it's a bit tricky, but it's actually absolutely doable. And the other thing is, the whole idea is to stop the appearance of resistance. This seems to be a good way to do it. But once again, it's not all pink, and the bacteria might find a way to resist the drug because we're still trying to stop the normal way of functioning, so we're going to try to avoid this. But the hope is it will take 20, 30 years before we see any resistance happening instead of 6 months. And beyond all this talk about bacteria and drugs, if there's a take-home message I'd like to give is, what I really like about the story is really people taking a step back from what we've been doing for 80 years and go and say, wait a minute, there might be a smarter way. This is obviously not working, and we've been blindfolding our eyes for the last 40 years, but maybe it's time to just take the mask out and just take the mask off and sit down and say, can we be smarter than this? In that case, can we just stop killing each other? That's it.
So if anyone has any questions, come down. We'll get back to you. Wilko will be happy to answer them. And also, this is very high tech, so I have a piece of paper here. And if you want to fill in your name, email address, so I can send you an email about the next NerdNite, so you know. And also, if you are nerds about something in particular, you can also tick the box here if you would like to give a presentation as well. As you've seen, it involves beer and having a good time and just sharing your passion or whatever you nerd about. So I'm just going to pass it on. Wilko will answer some questions.
I was very excited.
And then you can get more beer afterwards, and there will be a bit of time for networking until around
like 1 a.m. At least like an hour.
Okay, an hour or a bit less, depending on what the mood is. So, a few questions for Wilko from the very excited people. Shall we start here and then go that way?
I really enjoyed the talk.
Okay.
I have a question for you about the biology.
Yeah.
But I have been reading a lot of studies about human resistance to antibiotics. It's being caused by the increased use of antibiotics in lifestyle.
Yeah.
I understand that right now you presented a slide with the increased interest in deciding from the research perspective, like how to convert from the typical antibiotics to this human medication.
Yeah.
I'm just curious whether these studies also involve the medication that we can receive into the livestock and to our
Yes.
diet.
So.
Wilko, could you just repeat the question for all those two people on YouTube, like the two ones that are going to watch the video?
Sure. So the question was, she's been reading a lot about the use of antibiotics in animal feed and how this antibiotic resistance gets converted to bacteria, and that with the food we eat, and then the antibiotic resistance happen to be in others. And yes, there is actually, could be a good solution because using antibiotics for animal feed has double consequences. First is for prevention of any infection happening, but also, and primarily, it promotes growth of the animal itself. I'm not an expert, but animals get bigger, get fatter, you get more, you can sell for more. And those drugs don't. They don't promote this growth factor. So we can hope that because it doesn't, then there will be much less interest from the agriculture technology to use it.
So there is hope, like if you said before that probably in 30 years there might be this alternative medication, there might be also applied to the livestock.
Exactly, well, it would be of less interest to use in livestock, so maybe they will use less. There's still probably some use some, but probably won't be as widespread as it is today. Yes.
Okay, as you well know, I am a biologist.
Yeah.
So I would like to know, how do you think the recent discovery of CRISPR fits into this story? Because CRISPR is meant to be kind of the great savior of humanity. There is still a lot of things going on there.
Well,
But for example, for this antibiotic resistance, do you think it's something good from this technique?
not really, because by CRISPR, I think you mean gene editing. So you're
Yeah.
able to take a gene out, or put a gene out in the DNA. Well, how do you do that in the bacteria? CRISPR works well because, I mean, in someone's guts. It's probably very able to do it in the lab, but can you do it in someone's guts?
Yeah, there are companies working on it.
Then in that case, that would be a good way to feed it. We'll have CRISPR to take out the gene responsible for the weapons. Because once again, you're not touching anything critical for the survival of the bacteria, so, okay, I lost a gene, but I'm not dead, so I can keep living and need to be resistant. Or maybe it will, we're still changing DNA, so resistance might still appear, but
Yeah.
it could be a good target for CRISPR. But that's very hypothetical, yes. Was there questions? That's in front.
Yeah, so I had a question about the resistance. So, like one of the big problems with
Yeah.
antibiotics is just the resistance, right? We can develop resistance, bacteria can develop resistance to the antibiotics, and you stated like this method of this kind of drugs will not. But I don't know. I want because I'm thinking, for example, like the thing that you said with the bacteria communicating with each other
Yeah.
to coordinate an attack or something
Yeah.
like that, right? So evolution is based on advantages. So if you get an advantage from a certain mutation, then you will have a higher chance to survive.
Yeah.
So if some of these bacteria are resistant to this kind of drug that don't allow them to communicate, then they will have an advantage. They will be able to infect and they will be able to reproduce better, right? So you can still develop resistance.
That's
to
what I
it.
said at the end. Because the hope is it will take 20 to 30 years because it's going to be just a mild inconvenience instead of trying to kill.
Yeah, okay, it's a much softer pressure.
Exactly. So the idea
Yeah,
is hopefully
okay.
we get 20. So if it takes 20 years or 6 months, then it gives us a bit of a head start to find the next drug instead of just rushing all the time in the race, in the arm race between us and the bacteria.
Okay, thank you.
Okay, so when you were talking about how it would, give us more time, I was thinking that actually if you really make peace with the bacteria, then the bacteria would not replicate and then they would not spread. And so would you like effectively vaccinate a generation of people who took this drug?
The issue is, the thing here is if you prevent inflammation, if you prevent disease, then the immune system will be able to focus and destroy the bacteria. So the idea is, you might that way create a vaccine.
It's like it's sort of like a larger scale vaccine.
Kind of. Well, you can, I guess, compare the principle because the bacteria will be an attenuated bacteria who is not able to make the disease. Like in a way, when you take a virus and take away all the infectious part, you just take the shell and use that as a vaccine because then you will see the immune system will recognize the shell of the virus and then be able to develop antibodies. So if we have a bacteria that's harmless, maybe then you can start to develop antibodies and keep it in your immune memory. And it could be.
But I mean, if you give this drug to people who are not even sick yet, then
well, no, because as I said, they have to be very specific because they target weapons.
okay, right.
So if you
it's
don't
not
have bacteria
right.
with the weapons, that would be some would be
Okay.
useless.
I wonder if you could give that.
Any more questions?
I have one.
Last one.
No, just because there are no, I have no idea. So the thing is,
Yeah.
there is no, you said it's they're very specific weapon, so
Yeah.
there is no hope that you can find a general way of how their research works.
Usually no. Well, no, it's like so far it's, as I said, it's thousands of different species of bacteria, so you might find something common to 4 or 5 different species, but trying to find something that will be common to 50 species is going to be pretty much impossible. well, DNA with every bacteria's DNA. So if you find some critical part of the DNA, that's going to be everywhere. Or, for example, the membrane, that's the envelope around the bacteria, as also as a common baseline. So if you can target the baseline, you can find a way to kill the bacteria. So weapons, it's tricky.
Okay, thanks very much, everyone. It's beer o'clock again. So